Energy. So there's matter and there's energy. Energy is different than matter. Energy is not matter. One way to define energy is the capacity to do work. One of the things that can be a little confusing is we use words in science a little differently than we may use them in everyday life. And sometimes the definitions overlap, but in other ways they're different. Energy is the capacity to do work, the ability to do work. And what is work? Work is defined as the result of a force acting on a distance. So if I take this remote control and I push it across the bench top, I have exerted a force on this over a distance. I just did work. It's a little different than our definition of work in everyday life, where that usually involves being paid to do something that maybe you don't really want to do, right? I'm lucky I get paid to do something that I love to do. I'm like, wow, I get to go there and teach students and they give me money? Like, wow, that's fabulous. But work is a force acting on a distance. The behavior of matter, the reason that matter combines, why does butane burn in air? It has to do with energy. Energy is the driving force behind the behavior of matter. So we have to understand some things about energy in order to understand chemistry and how and why atoms do what they do. So we just talked about matter being conserved. Well, energy is also conserved. So the law of conservation of energy, very similar to the law of conservation of mass or matter. Energy is neither created nor destroyed. You can't make energy out of nothing. It also doesn't disappear into thin air. The total energy content of the universe is constant. But you can transform energy from one form into another. And energy can be transferred from one object to another. Some forms of energy are more useful than other forms of energy. What are those different forms of energy? And you need to have a basic idea of what these types of energy are. So maybe we'll use the highlighter here. So kinetic energy is energy associated with motion. So when something is moving, it has kinetic energy. The faster it moves, the more kinetic energy it has. And that kinetic energy applies to movement not only that is where you're traveling, but also just wiggling. And so you guys all have energy right now, even if you feel like you don't, because you're all moving. So you all have some kinetic energy. Potential energy is energy associated either with position or with composition. So position is, like here I've got my Sharpie, and when I raise it above the bench top, it has potential energy. If I lower it down to the bench top, it has less potential energy, because when it falls, if it falls off the bench, it's going to fall less far than if I'm holding it out here. So the higher it is off the ground, the more potential energy it has. So that's position. Composition is also potential energy. Why do we put gasoline in our cars? To get energy to make the car move. Well, the energy in the gasoline is a potential energy based on the position of the atoms arranged in the molecules of the gasoline. It's a potential energy, and it can be released and transformed into other types of energy. Then we have electrical energy. This has to do with the flow of electrical charge. We have thermal energy. Thermal energy is random motion of matter. Thermal energy is a type of kinetic energy. And then we have chemical energy. Chemical energy is a form of potential energy associated with the positions of the particles that compose a chemical system. Gasoline has potential energy in the form of chemical energy. So the total energy of a sample of matter is the sum of the kinetic energy plus the potential energy. So if we look, here's a picture of a dam. Here's a reservoir, and here's the dam, and then you can let water through the dam and it falls down. So here we're looking at the side of the dam. On the lake side, the reservoir side, this water has high potential energy due to its position. If we open the gates on the dam, this water is going to flow down. This has more potential energy than the water down here has. This water is going to just slowly flow down the stream, but it's not going to fall quickly like this energy does. As this water flows down, its potential energy is transformed into kinetic energy as it moves faster and faster and faster. I think I've got a different picture coming up for that. No? Where'd it go? Sorry, that was the other class. But let's look at this marker again. So when I hold the marker out, it's got potential energy. When I release it, it falls. As it falls, it's falling faster and faster and faster, and its potential energy as it gets closer to the desk is going down. Its speed is going up. But then the question is, what happened to that energy? Where'd it go? It splattered. Yeah, it did. It was transformed into heat energy when it impacted the bench. You're like, well, it doesn't feel hot. Yeah, well, there wasn't a lot of kinetic energy or potential energy. It was a small amount. But if you get two things that are large enough and they collide into each other, they can generate quite a bit of heat. The energy was not lost. It didn't disappear, but it was transformed from potential energy to kinetic energy and then into heat energy that dissipated into the air around it. Well, energy is a quantity that can be measured, so we have to have some units. So these are units of energy. Joule. That's a lowercase j. One of the things I don't like about this font, but overall I like it. That's lowercase j. Joule, named after a scientist. The abbreviation is capital J. That's the SI unit or the metric unit of energy. Then we have the calorie with a small c and a calorie with a capital C. We've heard about calories, right? Candy bars have calories and they'll make you fat, right? Well, that's the nutritional calorie, which is a calorie with a capital C. It's abbreviated capital CAL. And this is actually equivalent to 1,000 of these smaller calories. So in other words, this is actually a kilocalorie. The calorie that scientists refer to is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. That's how we define a calorie. And then another unit of energy is kilowatt hours. And that's what PG&E uses to measure how much electricity your house is using, kilowatt hours. So here's a useful table expressing the relationship between some of these units. The calorie is 4.184 joules. This nutritional calorie with the big C is 1,000 of the small c calories. And this is just kind of for information. Kilowatt hour is a whole bunch of joules, 3.6 million of them actually. You do not need to memorize these conversions, but we do need to know how to use them and convert energy units. So the complete combustion of a small wooden match produces approximately 512 calories of heat. How many kilojoules are produced? Well, we need to look up some conversions. So they're giving us calories, they're asking for kilojoules. There's no kilojoules on here, but here's a relationship between calories and joules, 4.184. So I'm just going to write that down before I forget. 1 calorie equals 4.184 joules. This ends up being a unit conversion problem. So we've got 512 calories. That's what we're starting with. And what unit are they asking for? Kilojoules. How do you think we'd abbreviate that? KJ. Lowercase k, uppercase j. We know a relationship between calories and joules, so we could go from calories to joules. Could we go from joules to kilojoules? Yeah, because we have learned the metric system, haven't we? Just smile and nod. Oh yeah, we got that down. Kilo is a prefix that means 10 to the third, and it can apply to any unit. So we've got our path, calories to joules to kilojoules. We write out the units, 512 calories to joules to kilojoules. 2 arrows, 2 conversion factors. We take the previous unit and put it on the bottom because we want those to cancel out. After we get all the units in place, we put the numbers in. So 1 calorie, 1 in front of calorie, 4.184 in front of joules, 4.184. And then over here, I did this in lab for somebody yesterday and it seemed to help out. Kilo means 10 to the third, because that's what everybody decided. So you just have to memorize that. All of these conversion factors are equal to 1. We're multiplying by things that are numerically equal to 1. We're not changing the quantity, we're just changing the name, right? And so remember, 12 inches per 1 foot. 12 inches is just a different name for the length that is 1 foot. So our conversion factor here of kilojoules and joules, the top has to equal the bottom. So if I put joules over joules, is that equal to 1? Yeah, anything divided by itself. What if I put kilojoules over kilojoules? Is that equal to 1? Yeah. Now, what if instead of the K, I write what it means? What if I take this K on the bottom and write 10 to the third instead? Is that still equal to 1? Yeah, because K means 10 to the third. This is the conversion factor I need here. I've got K on the top. Why? Because my path told me that's what I needed. When I put the number in, I put the number in on the other side. So I put the 10 to the third down here. And I'm going to say 1 times that and 1 of those. Calculator hiding. So 512 times 4.184 times 1 divided by 1 EE3 equals. Calculator says 2.142208. And the unit would be kilojoules. How many significant figures? 3. 512 calories is a whole number that does not mean it's exact. This has 3 significant figures. This has 4. This is exact. So I'm going to keep 3 significant figures and round this to 2.14 kilojoules for my answer. Any questions?